Welcome to our virtual learning in statistics. Section 6.2, confidence intervals for the mean, sigma unknown. This is a review of how to construct a confidence interval for a population mean when sigma is unknown. The first thing you need to verify is that, well, you don't know sigma. Sigma is not known, but you need to verify that the sample is random, and one of two things, either that the population is normally distributed or approximately normally distributed, or in the case the population is normally distributed, then you need to have that the sample size is greater than or equal 30. Remember that when the sample size is greater than or equal 30, then independently of the distribution of the original random variable, the distribution of the sample means is going to be approximately normal. In that case, you will use sample mean and sample standard deviation to calculate the t-statistic. And if the population is normally distributed, then even for sample sizes less than 30, you can use the sample mean and the sample standard deviation to calculate the t-statistic. Once you verify this, then you need to find the sample size, the sample mean, and the sample standard deviation. For the sample mean, you know the formula to calculate it, and for the sample standard deviation, you also know the formula how to calculate it. Then we need to identify the degrees of freedom. Remember that the degrees of freedom are one less than the sample size, and you need to set the level of confidence, C. Once you have the level of confidence C, then you use the table for the critical values of the t-distribution to find the critical values associated to the level of confidence. Once you have the level of confidence, then you need to find the margin of error, E. For this, you have this formula here, which is pretty similar to the formula that we use in the case when we have sigma known. Two main differences. First of all, we don't have the critical values for the C distribution, but for the T distribution in this case. And here, instead of having the standard error of the mean, you have an estimation of the standard error of the mean, which is built by putting in the numerator the sample standard deviation and on the denominator the square root of the sample size. Once we have the margin of error, then we proceed as in the previous section to find the left endpoint of the interval. You take the point estimate minus the margin of error, and to find the right endpoint, you add to the point estimate the margin of error, and then you have your interval. Okay, and then you will say with certain level of confidence the population mean will be contained in the interval, and the interpretation is the same. If we build several intervals using this procedure, then about C% of those intervals will contain the population mean. Example: constructing a confidence interval. In these examples, we need to read carefully to verify first this. Okay, we need to verify that the sample is random. We need to verify whether or not the population is normally distributed or almost normally distributed, or if the sample size is large enough. You randomly select 16 coffee shops, so n is going to be equal 16. N is going to be equal 16. When we see n equals 16, we know that at some point in the statement of the problem, we need to find that the original random variable is normally distributed, because this is a small sample size. So you randomly select 16 coffee shops and measure the temperature of the coffee sold at each. So you have your 16 data points. The sample mean temperature is 162 Fahrenheit degrees. So this is your point estimate, with a sample standard deviation 10 Fahrenheit degrees. This is your estimation for the population standard deviation. We need to construct a 95% confidence interval, so this is the value for C. 95% confidence interval for the population mean temperature of coffee sold. And again, this is extremely important. Assume the temperatures are approximately normally distributed. Once we know that, then we know that for this sample size, 16, then we can use the t-distribution to build the confidence interval. Sigma is unknown, the sample is random, and the temperatures are approximately normally distributed. Then we can use the t-distribution. N equals 16, square root of 16 is 4. We use this value as the point estimate, and this as the estimation of the standard deviation of the population. The level of confidence is 95%, and the degrees of freedom are 15 because n is equal to 16. So if we use the table to find the critical value, we'll find that is 2.131. Let's just verify that this is the value. If we go to the table that we presented in the previous example, degrees of freedom are 15, level of confidence is 95, then we look for the value here, and this is 2.131. So now the margin of error for the 95% confidence level is, and then we use the formula to calculate it. This is the critical value associated to the 95% confidence level. This is the estimation of the standard deviation of the population, and this is the square root of the sample size. So the margin of error is approximately 5.3 Fahrenheit degrees. To build the confidence level, we just need to subtract and add the margin of error from the point estimate. And if we do that, we find this interval here. We can graph it as well as we did in the previous section, and then we can say with 95% confidence, you can say that the mean temperature of coffee sold is between these two values. Okay, so with 95% confidence, remember what that means. That means that if we repeat this process several times and we produce a family of intervals, then 95% of those intervals will contain the population mean. Next example. Example, constructing a confidence interval. You randomly select 36 cars. So again, random sample, n is equal 36 now, is equal 36, which is greater than or equal 30. We may or may not find in the statement of the problem that the original random variable is normally distributed. If we find it, it's okay. If we don't, it's okay as well, because now we have n greater than or equal 30, and therefore the central limit theorem guarantees that the distribution of the sample means is going to be approximately normally distributed, and then even if the standard deviation of the population is not known, we can use the estimation produced by the sample standard deviation to calculate the t-statistic. Alright, so you randomly select 36 cars of the same model that were sold at a car dealership and determine the number of days each car sat on the dealership lot before it was sold. The sample mean is 9.75 days. This is going to be our point estimate, with a sample standard deviation 2.39 days. This is going to be the estimation for the population standard deviation. We would like to construct a 99% confidence interval for the population mean, number of days the car model sits on the dealership lot. Solution. because sigma is unknown, the sample is random, and the sample size is greater than 36, then we can use the t-distribution. So if we use n equal 36, this will be the point estimate for the mean, this will be the estimation for the standard deviation of the population, this is the level of confidence, and the degrees of freedom are going to be 1 less the sample size. Now, we use the table to find the critical value for the 99% level of confidence, okay? And then we can build the margin of error using the formula. So it will be the critical value of the t-distribution for the 99% level of confidence, the sample standard deviation divided by the square root of the sample size. And this is approximately 1.09. Then, to build the confidence interval, we just subtract and add the margin of error from the point estimate of the mean. So we get this interval that we can graph like that. Now, the question remains, when to use the normal or the t-distribution? So for that, it will be a good idea to follow this diagram. You need to ask yourselves when you are reading the statement of the problem, is the population normally distributed, or is the sample size greater than or equal 30? You need at least one of them. If the population is normally distributed, yes, then you go on here, or if the sample size is greater than or equal 30, yes, then you go on here. If the answer is yes to either one of these, then the next question is sigma known? If sigma is known, yes, then you go to this and you use whatever theory we learned in section 6.1. If the answer is no, if sigma is not known, then you use whatever we have learned in section 6.2. Example, normal or t-distribution. We're going to read carefully this statement and we're going to find out if we need to use the normal or the t-distribution. You randomly select 25 newly constructed houses. We know that the sample is random, good. We know that the sample size is 25. If the sample size is 25, then, since this is less than 30, we'll need to find somewhere in the statement of the problem that the population is normally distributed or approximately normally distributed. The sample mean construction cost is 181,000. This is going to be the point estimate. And the population standard deviation is 28,000. So here the population standard deviation is known to be 28,000. Assuming construction costs are normally distributed, this is good, right? Because the sample size is less than 30. Should you use the normal distribution, the t-distribution, or neither to construct a 95% confidence interval for the population mean construction cost? Explain your reasoning. Is the population normally distributed or n is greater than or equal 30? Well, n is not greater than or equal 30, but the population is normally distributed, so the answer is yes. The population is normally distributed. Note that, even though the sample size is less than 30, you can still use either the standard normal or the t-distribution because the population is normally distributed. How do we know which one to use? We need to answer the next question. Is sigma known? Yes. Then use the standard normal distribution and all the theory that we learned in section 6.1.